When the sky turns deadly, could a nearby star rewrite our story? If a nearby star exploded tonight, what would you actually notice? A beautiful new point of light in the sky, or the quiet beginning of the next mass extinction on Earth? We like to think of supernovae as distant fireworks. Spectacular, yes, but safely happening out there, somewhere, in the vastness of the universe. Yet there is a specific distance, measured in light years, where that comforting picture breaks. Beyond it, a supernova is just a show. Inside it, the same event can rewrite the story of our planet. This means that, in principle, one stellar death could decide whether our own civilization gets a sequel. It should be noted that this danger zone is not just a theoretical line drawn on a blackboard. When we drill into Earth's rocks and deep-sea sediments, we find strange fingerprints, radioactive iron atoms, forged in supernovae that arrived here within the last few million years. They hint that Earth has already been brushed by nearby blasts, not close enough to sterilize the surface, but close enough to raise the question, did exploding stars once help trigger mass extinctions, or reshape the path that life took on this planet? And if one went off tonight, your first warning would not be light at all. Before the sky brightened, before telescopes saw anything unusual, a ghostly wave would sweep through you. Trillions of neutrinos, almost massless particles from the collapsing core of the star, would cross your body, your home, and the entire Earth in a fraction of a second. You would feel nothing, no heat, no pressure, no sound. But our detectors would. In the hunt for alien life, we often talk about listening for faint radio signals. Here, we would be listening for the universe shouting through neutrinos that a nearby star has just died. Only minutes to hours later would the high-energy radiation and, finally, the visible light arrive. By the time we saw a new star bloom in the night, the real story would already be underway in our upper atmosphere. Ozone molecules could be broken apart. Cosmic rays could begin to rain down. The question is not just what we would see, but what would happen silently above our heads, to the shield that makes Earth habitable. And we live in a galaxy full of dying stars. Some even have familiar names: Betelgeuse in Orion, Antares in Scorpius, Eta Carinae, far more massive and unstable. For many of them, the real question is not if they will explode, but how close we will be when they finally do. So, it's time to find out the truth. How near is truly dangerous? Which stars in our local system are the real threats, and which are harmless celebrities? So, let's begin. Next, we will pin down actual danger distances, meet our nearby supernova candidates, and walk step by step through what the next galactic blast would do to our atmosphere, our technology, and maybe to our species itself. Why supernova distance matters more than raw power there is a twist here that sounds almost paradoxical. A nearby star can unleash more energy in a single explosion than our sun will in its entire 10 billion year lifetime, and yet, from Earth, it might be nothing more than a spectacular new point of light in the sky. How is that possible? The raw power of a typical core collapse supernova is staggering, around 1046 joules of energy. This means that in a few seconds, the dying star outshines its whole previous life. But while that sounds instantly apocalyptic, space is vast. Energy spreads out as it travels, thinning into an ever larger sphere. By the time that violence has expanded over tens, hundreds, or thousands of light years, most of it has simply diluted into the background glow of the universe. So distance is everything. Instead of asking, how big is the explosion, we have to ask, how close is it to us when it happens? Modern models suggest a kind of invisible danger zone around any supernova candidate. Inside roughly 10 to 30 light years, the high-energy photons and cosmic rays become intense enough to seriously damage a planet's atmosphere. Outside that, the same blast mostly becomes a light show. It should be noted that these numbers are not sharp cutoffs. At the inner edge, within about 10 light years, we might be looking at severe ozone depletion, a dramatic spike in ultraviolet radiation at the surface, and a real threat to complex life. Between 10 and perhaps 30 light years, the risk is still serious, especially for the upper layers of the biosphere. Out toward 50 light years or more, the effects look milder: subtle climate nudges, slightly elevated radiation, maybe long-term evolutionary pressure rather than instant catastrophe. And this is not just theory. In deep-sea crusts on Earth, scientists have found radioactive isotopes like iron-60 and plutonium-244 that should have decayed away long ago. Their presence is a fingerprint of recent cosmic explosions, probably at distances of a few hundred light years within the last 10 million years. Some researchers link these events to shifts in climate and possible extinction pulses. In the hunt for alien life, we often talk about a habitable planet sitting in a Goldilocks zone around its star. But supernovae remind us there is also a larger galactic environment quietly shaping who survives and who does not. Optimistically speaking, Earth has clearly made it through previous blasts. But while the overall picture is becoming clearer, the details are still uncertain. Different types of supernovae, different orientations of any jets, and different states of Earth's atmosphere all change the threshold distances. This means we are dealing with probabilities and scenarios, not simple yes or no answers. So it's time to find out the truth about our own neighborhood. Which specific stars around us are close enough and dangerous enough to cross that line from spectacle to catastrophe? In the next part, we will point to real stars in the night sky and ask a very personal question. When they die, do we live? Meet the suspects, Betelgeuse, Spica, and other stellar time bombs. So, if the line between spectacle and catastrophe is written in light years, which actual stars are we talking about? And when we look up at the night sky, are any of those bright points already primed to explode in our lifetimes? Let's start with the celebrity of stellar doom, Betelgeuse in Orion. This red supergiant is a bloated, dying star, swollen out to hundreds of times the size of our sun and shedding material into space. It sits roughly 550 to 650 light-years away, close enough that we feel an odd sense of intimacy with it. When Betelgeuse dimmed dramatically in 2019 and 2020, rumors exploded that it might be about to go supernova any day now. It should be noted that on astronomical timescales, any day now means sometime in the next 100,000 years. So, is Betelgeuse dangerous for our technology, for our atmosphere, for life on Earth? The data say no. Even though it will almost certainly end as a core collapse supernova, its distance puts it far outside the true danger zone, which most studies place within roughly 10 to 30 light-years. When Betelgeuse finally blows, it will be a once-in-a civilization light show, perhaps brighter than the full moon and visible in daylight. This means it would transform our sky, not wipe out our biosphere. Optimistically speaking, it might even inspire a whole new generation of astronomers. But Betelgeuse is not alone. Take Spica, the bright blue star in Virgo. Spica is actually a massive, hot binary system about 250 light-years away, with stars that are far more luminous than the Sun and destined for violent ends. Or Antares and Scorpius, another red supergiant, similar in spirit to Betelgeuse and roughly 550 light-years distant. These are true monsters by mass and energy output, yet even they are simply too far away for their eventual explosions to be truly life-threatening. They would shower us with beauty, not extinction. Pattern interrupt? What about the really exotic stuff? Eta Carinae, for example, is an unstable, incredibly massive binary star system about 7,500 light-years from us. It has already survived a 19th century eruption that briefly made it one of the brightest stars in the sky. If anything in our galaxy is a candidate for a spectacular, possibly jet-driven explosion, it is Eta Carinae. And yet, it is so distant that even its most dramatic fate would be a cosmic fireworks display, not an atmospheric disaster. So, let's begin to face a more unsettling possibility. The stars that are close enough to be dangerous are, paradoxically, not the famous names we already worry about. They might be ordinary-looking, less studied, and hiding in plain sight. So it's time to find out the truth. Could there be a ticking stellar time bomb much closer to us, quietly waiting for its moment? In the next section, we will ask how close is too close, and whether our own neighborhood hides a threat we have barely mapped. The invisible trigger, how a supernova actually explodes, if there really is a ticking stellar time bomb nearby, what does it actually mean for that star to explode? Most of us picture a sudden flash in the sky, but the true trigger is invisible, silent, and over in less than a second. Massive stars live fast and die violently. While a star like the Sun quietly fuses hydrogen for billions of years, a star 8, 20, or even 30 times more massive burns through its fuel in a cosmic rush. It stacks elements in its core like an onion, hydrogen to helium, helium to carbon and oxygen, then heavier and heavier nuclei. But there's a hard stop. When the core builds up iron, fusion no longer pays the energy bill. This means the core is suddenly supporting a star's weight with nothing left to push back. So, what happens when gravity finally wins? The iron core collapses in on itself, accelerating to a significant fraction of the speed of light. In milliseconds, a region the size of Earth is crushed down to a neutron star only tens of kilometers across. The imploding core slams into this ultra-dense object, rebounds, and sends a shockwave racing outward through the infalling layers. It should be noted that this first shock, by itself, is not yet the glorious explosion we see in space images. Left alone, it would actually stall. The real power source is even stranger. As the core collapses, it releases an enormous flood of neutrinos, ghost-like particles that barely interact with normal matter. Roughly 9% of the total energy of a core collapse supernova leaves as neutrinos in just a few seconds. They stream out almost unhindered, some of them re-energizing the shockwave and finally blowing the star apart. From a physics point of view, that neutrino burst is the true moment of explosion. Those particles race outward at nearly the speed of light, reaching any nearby planets hours before the star brightens. If a star in our own neighborhood went supernova, the first hint on Earth would be a sharp spike in our underground neutrino detectors, long before anyone could step outside and see anything different. So it's time to find out the truth. Our earliest warning would be a wave of particles passing straight through our bodies. After that comes the light. Within minutes to hours, the shock punches through the star's surface, unleashing a flash of X-rays and gamma rays. Then, over hours to days, the shattered star swells into a supernova, bright enough to rival an entire galaxy. Its ejecta expand over years, then millennia, cooling and mixing heavy elements like iron, gold, and uranium back into the surrounding system. Each phase of this chain reaction interacts with a habitable world differently. Neutrinos as subtle particle showers, high-energy photons that can erode an atmosphere, and long-term radioactive debris that may alter climate. In the hunt for alien life and for our own survival, we need to ask, at what distance do these invisible processes start to reshape a planet's history? In the next section, we will bring this down to Earth and ask how close is truly dangerous for us. Is it a light show or an extinction event? So if a nearby star really did explode in our lifetime, what are we actually talking about here? Would we step outside and see a glorious new guest star blazing in the sky, or would we be living through the opening chapter of a slow-motion extinction event? This is the central tension. There is a distance, measured in light years, where a supernova flips from spectacular to dangerous. Beyond that line, it is mostly a cosmic fireworks display. Inside it, the atmosphere itself begins to change, and with it, the prospects for life on the surface. So, let's begin by sketching those two futures. Imagine the blast goes off about 100 light-years away. That is far in human terms, but in our local stellar system, it is still very much the neighborhood. In this case, we would see an incredibly bright new point of light, rivaling the full moon at its peak, visible even in daylight for weeks. Instruments would record a modest rise in cosmic rays, and high-energy photons would brush the top of our atmosphere, but models suggest Earth's ozone layer would only be slightly disturbed. For us, it would be a story in the news, not the end of the story. Now move that same event inward to 10 or 20 light-years. The energy arriving at Earth grows by more than an order of magnitude. This means the upper atmosphere is hammered by gamma rays and X-rays, splitting apart molecules of oxygen and nitrogen. Chemical chains begin to deplete ozone, the protective shield that blocks the sun's harsh ultraviolet light. It should be noted that several studies predict ozone losses large enough to significantly increase at the surface for thousands of years. What does that feel like on the ground? Not instant firestorms, but a subtle, planetary sunburn. Higher levels stress plankton in the oceans, damage plant tissues on land, and raise mutation and cancer risks in animals. Ecosystems bend under that pressure. Some may break. Optimistically speaking, life is resilient and can adapt. But at these distances, we are no longer talking about a harmless light show. We are talking about a biosphere experiment imposed by a distant star. So, it is time to find out the truth. The real question is not simply, could a nearby supernova hurt us? It is where exactly is the line in space where beauty becomes hazard, where a habitable Earth-like world starts to be reshaped by the sky, and do any stars we know actually sit inside that danger zone right now? Intriguingly, our planet may already hold a clue. Layers of deep-sea crust contain traces of radioactive iron-60 and plutonium-244, isotopes that decay quickly on cosmic timescales. Their presence suggests that at least one supernova went off close enough in the last few million years to dust Earth with debris, yet not close enough to sterilize the surface. In the hunt for alien life, and for our own survival, this is a powerful hint that the line between spectacle and disaster is real. In the next segments, we will try to pin that line down. We will put numbers on those distances, us, walk through what actually happens to Earth's atmosphere step by step, and ask how much warning our modern detectors would give us before the sky changes forever, or whether the first sign would arrive too fast to see coming. Who's watching the sky for us? Detectors, telescopes, and early warnings. So, if a nearby star did cross that invisible line, who would actually see it first? It would not be us, staring up at the sky. It would be a network of silent machines buried deep underground and frozen into Antarctic ice, watching for ghosts. Evaluating the real danger from a supernova means tracking more than just light. Almost all of the energy comes out as neutrinos, those nearly massless particles that pass through an entire planet as if it were smoke. So, let's begin with the detectors that wait in the dark. In Japan, supernovae is a giant tank of ultra-pure water, lined with thousands of sensitive eyes. When a rare neutrino does interact, it creates a tiny cone of blue light, a whisper of the star that produced it. At the South Pole, IceCube uses a cubic kilometer of clear ice as its detector. Strings of sensors are frozen deep below the surface, listening for faint flashes when neutrinos strike the ice. Under normal conditions, these instruments see a slow drizzle of events, but while that background is steady, a galactic supernova would change everything. In the first second of collapse, the dying star would flood the universe with neutrinos. Here on Earth, supernovae, IceCube, and other observatories would suddenly register thousands of detections. This means a clear, unmistakable spike in their data, rising in just a heartbeat. It should be noted that this flood would arrive hours before the first visible light from the explosion. That is where the Supernova Early Warning System, or SNOOS, comes in. As soon as multiple detectors see that spike, SNOOS automatically sends an alert to astronomers worldwide. Telescopes would know something has just died in our galaxy, even though the sky still looks normal to the human eye. Then, the photon chase would begin. Space telescopes and all sky monitors in X-rays and gamma rays would swing toward the suspected region. Optical survey telescopes on Earth would be primed to catch the first brightening as the shockwave reaches the star's surface. From the first high-energy flash to the slow fade of the debris cloud, we could track the entire event in real time, frame by frame. For a star within a few tens of light years, that early warning is mostly informational. We cannot shield the whole atmosphere, but we could power down sensitive satellites, adjust astronaut activities in orbit, and prepare to watch the physics unfold in exquisite detail. Optimistically speaking, it would be the most studied catastrophe in history. Pattern interrupt for a moment. Imagine an alien civilization orbiting a distant, habitable planet around a quiet red dwarf. In the far future, they might build their own supernovae, their own ice cube, and one day watch our sun go supernova. To them, our final flare would be data. So it's time to find out the truth about our own preparedness. In the next section, we will take that warning signal and ask what, exactly, it buys us when deadly radiation finally reaches Earth. Your host, today's mission, and the roadmap through a cosmic disaster. So, if our warning is just a ghostly whisper of neutrinos, who's actually listening? And where are we going with all of this? We should be clear about the journey before we step into the blast zone. And this is our channel, where we take focused, high-stakes questions about the universe and turn them into guided tours you can actually follow. Today's mission is one very specific what-if, not just any exploding star, but a supernova close enough that it stops being a pretty light in the sky and starts being a force that could rewrite Earth's history. So, let's begin by building the toolkit we need. What exactly is a supernova in energy terms, not just drama terms? How does a blast that releases around 10 joules become either a harmless fireworks show or a planetary-scale hazard, purely depending on distance? This means we'll talk about that crucial danger zone, roughly 10 to 30 light-years, where the difference between a spectacle and a biosphere crisis is measured. It should be noted that we already have early warning systems, neutrino detectors like supernovae and IceCube, and space telescopes watching massive stars on the edge of collapse. We will see what those instruments would tell us, and how many precious hours or days they might buy. Once we have that foundation, we will walk through the disaster as if it were happening to us. What would the very first moment look like from Earth's point of view? First, the invisible neutrino wave silently passing through your body, then the flash of high-energy photons, followed by the bright optical peak that could outshine the full moon. And finally, the long radioactive tail as debris sweeps through our region of the galaxy. Step by step, we will build a timeline you can almost experience, minute by minute, then week by week, then century by century. After that, we zoom out from the sky to the air we breathe and the life that depends on it. How does that radiation carve into our atmosphere, strip ozone, and let extra ultraviolet light pour down to the surface? Could cosmic ray showers seed clouds, damage DNA, and echo the signatures we see in ancient rocks, like layers rich in radioactive iron-60 that may record past supernovae and perhaps even mass extinctions? In the hunt for alien life, we often think about what distant stars might do to their planets. Here we turn that same logic back on ourselves. Finally, we will confront risk and agency. Which nearby stars are actual candidates? Betelgeuse, Spica, Antares, maybe Eta Carinae, and which ones only look dangerous from our backyard? Optimistically speaking, what are the odds on human timescales? And what, if anything, could we do to harden our technology and society against such a rare but immense event? So it's time to find out the truth. By the end, when you look up at a bright dying star, you will know, quantitatively, whether it is a reason for awe, worry, or both. Supernova 101, energy, distance, and why space usually saves us. To really answer that, we have to step back and ask a simpler question. How does something this violent actually fill space? Because a supernova is not a laser pointed at Earth, it is more like two very different explosions you already know. Imagine a hand grenade going off a few meters away versus a nuclear bomb detonating in the middle of an empty desert hundreds of kilometers from you. Which one is worse for you personally? The smaller blast right next to you is far more dangerous than the distant giant, simply because of distance. A supernova is the nuclear bomb in the desert, scaled up to a whole star. The total energy is staggering, but that energy has to spread out over an ever-growing sphere. This means as the blast races outward at close to the speed of light, it paints a larger and larger bubble around the dying star. The farther you are from the center, the more thinly that energy is smeared across the surface of that bubble. This is where the inverse square law quietly saves most of the universe. The surface area of a sphere grows with the square of the distance from the explosion. Double the distance, and the same energy is now spread over 4 times the area. Move 10 times farther away, and you only receive 1/100th of the intensity. It should be noted that this applies to light, to X-rays, to gamma rays, to almost everything that flies out of a supernova. So, let's begin separating types of stellar deaths. Because not all blasts are born equal. Core collapse supernovae happen when a massive star burns through its fuel, its core implodes, and the outer layers rebound violently. Thermonuclear, or Type 1, events occur when a dense white dwarf in a binary system steals matter from a companion until a runaway fusion reaction tears it apart. Both can outshine an entire galaxy for a short time, but they live in different neighborhoods and leave different debris. But while the star sets the power of the explosion, the planet sets what that power actually does. The same supernova, at the same distance, will not treat every world equally. A bare rock with no atmosphere is like standing directly in the radiation. It simply absorbs or reflects the blast. A planet with a thick atmosphere and a magnetic field, like Earth, filters and redirects much of the incoming energy. Earth's magnetosphere bends charged particles away, while our dense air soaks up high-energy photons and cosmic rays. In the hunt for alien life, that kind of shielding is part of what makes a world habitable, but it also creates new vulnerabilities. Ionization in the upper atmosphere can shred ozone, alter chemistry, and let more ultraviolet light reach the surface. So it's time to find out the truth. Before we talk about power grids, mass extinctions, or spectacular sky shows, we must start with the star itself. What type of star is it? How far away is it? And which explosion mode is it heading for? Only then can we translate a distant stellar death into concrete consequences here on the ground. The danger zone, mapping a kill radius in light years. So, if a supernova goes off in our cosmic neighborhood, where is the actual line between spectacular light show and planetary disaster? There is, quite literally, a kill radius in light years, and the uncomfortable truth is that it cuts right through the space around our own solar system. Astronomers have tried to turn that vague fear into hard numbers. When we focus on core collapse supernovae, the kind that mark the death of a massive star, current models put the zone of serious biosphere damage at roughly 10 to 30 light years. Inside this shell, the blast of high-energy photons and the long rain of cosmic rays could strip away tens of % of our ozone layer. This means ultraviolet light at Earth's surface might double or even triple for years. What does that actually look like on the ground? The sky would host a brilliant new star, bright enough to see in the daytime, but while we stared upward in awe, the atmosphere would be quietly rewired. More UV means more DNA damage, more skin cancers, more stress on plankton near the ocean surface. It should be noted that we are not talking about a single flash and then safety. The cosmic ray afterglow could last tens of thousands of years. Step a little farther out and the picture softens, but does not vanish. Many studies outline a wider, noticeable, but not catastrophic zone extending to perhaps 50 to 100 light years. In this region, ozone depletion might be modest, yet still enough to alter climate chemistry. Extra cosmic rays could seed more clouds, tweak rainfall patterns, and slightly raise mutation rates without collapsing entire ecosystems. Optimistically speaking, life is resilient. Earth-like biospheres have endured a lot worse from within their own Goldilocks zone. But there is a twist. Not all stellar explosions are spherical. Beamed events such as gamma-ray bursts focus their energy into narrow jets. If one of those jets were aimed directly at us, the dangerous range could leap from a few tens of light years to thousands. Atmosphere loss, global fires, a true mass extinction event suddenly become plausible. So, let's begin by calming one fear. We do not know of any nearby stars with gamma-ray burst jets currently aligned toward Earth. All of these thresholds are fuzzy. They depend on how energetic the explosion is, how dense the interstellar medium is between us and the star, and even on the state of our own atmosphere when the shock arrives. Still, they give us a working map. Inside about 10 light years is very bad, 10 to 30 light years is genuinely risky, and beyond that, the threat drops quickly. So it's time to find out the truth. If the real kill radius is that small, why do we see traces of supernova debris in Earth's rocks from events 50 to 150 light years away? And what did one particular blast, just 6 million years ago, really do to our planet? When the sky rained iron, Earth's past brush with a supernova, so how do we know a supernova ever brushed past us at all? To answer that, we have to leave the sky and go somewhere much less glamorous, the bottom of the ocean. Scientists drill cores out of deep sea crusts and sediments, layer by layer, like reading the tree rings of the planet. When they put those layers under incredibly sensitive detectors, they find something Earth should not be making anymore in any meaningful amount: radioactive iron-60 and plutonium-244. These atoms do not just appear out of nowhere. They are forged in the violent deaths of massive stars. It should be noted that iron-60 has a half-life of about 2.6 million years. If any had been around since Earth formed, it would have long since vanished. Yet we see a clear bump in iron-60, an ocean crust dating from roughly 2 to 3 million years ago, plus hints of earlier peaks. This means fresh material rained down from space relatively recently, on geological timescales. Where did it come from? When we map how these isotopes are distributed across different oceans and depths, the pattern points to one or more core collapse supernovae exploding within about 50 to 150 light years. The likely culprits are massive stars in nearby stellar associations such as Scorpius, Centaurus, a loose system of young bright stars that has been drifting past the solar system. We are essentially picking up their radioactive fingerprints, but while the isotopes are clear, the consequences are harder to read. Around the same time, at the Pliocene-Pleistocene boundary, Earth's climate was shifting toward cooler, more variable conditions, and several species of marine megafauna disappeared. Did the supernova trigger that? Or was it just one more stressor in a complex, changing climate system? In the hunt for alien life, we often talk about how delicate a habitable atmosphere can be. Here, we have a natural experiment on our own world. At something like 100 light years, Earth was not sterilized. There was no global firestorm, no complete collapse of the biosphere. Instead, our planet seems to have been dusted with radioactive debris, bathed in a slightly stronger flux of cosmic rays, and perhaps nudged in its atmospheric chemistry. Subtle, but not trivial. Optimistically speaking, that gives us a lower bound on what mild looks like. A nearby star can explode, and life keeps going. Pattern interrupt for a moment. Imagine a future geologist 50 million years from now drilling into what used to be our seafloor. They hit a resorphin layer rich in exotic isotopes, plastics, maybe even traces of our satellite's re-entry dust. They stop and ask, what cosmic event marked this strange technological slice of time? So, let's begin to turn that question back on ourselves. If a supernova 100 light-years away only dusted us, what happens if the next one goes off much closer than that? Minute by minute, the first hours of a nearby supernova. So, if a dangerously close star really does blow, what happens in the very first moments? Not years later in the fossil record, but minute by minute as we live through it on Earth. At T-Clux-O, in the star's own frame, its iron core collapses in a fraction of a second. Gravity wins, matter plunges inward, then slams to a halt and rebounds. This violent stop sends out a shockwave and, even more importantly, a blinding flash of neutrinos. These ghostly particles carry away about 99% of the explosion's energy, racing outward at almost the speed of light. We feel nothing. Our atmosphere, our bodies, the entire planet are transparent to them, but our detectors are not. Hours before anything changes in the sky, underground neutrino observatories would suddenly erupt with activity. Tanks of ultrapure water in Japan, ice buried under Antarctica, and liquid scintillators beneath Italy would all start recording thousands, maybe tens of thousands, of neutrino events in just a few seconds. Alarms would trip, automatic systems would cross-check the signal and push out a global alert. Astronomers' phones would light up at 3 a.m. While outside, the familiar constellations still look completely normal. This means the very first clue that a nearby star has died is an invisible wave passing straight through us. In the hunt for alien life, we often talk about listening for radio beacons, but here we are, listening for the death cry of a star. As the minutes tick by in the star's frame, the shockwave plows outward through its layers. When it finally reaches the surface, something dramatic happens. Shock breakout. For a few minutes to an hour, a flash of high-energy X-rays and gamma rays bursts into space. Space-based observatories, like Swift or Fermi, would catch this spike, even if the star itself were on the far side of Earth. It should be noted that for a supernova at a few tens of light-years, this pulse could slightly boost radiation levels in our upper atmosphere, stirring chemistry but not yet stripping it away. Then, the light we care about most begins to climb. Over the next hours to days, the expanding debris heats and brightens. On Earth, we would finally see a new point of light swelling in intensity. A once ordinary point in a constellation would turn uncanny, outshining every other star in the night sky. If the supernova is within our own galaxy and uncomfortably close, it could even become visible in daylight, a rival to Venus and perhaps nearly as bright as the full moon. Optimistically speaking, those first hours are more about awe than doom. Frantic telescope scheduling, wall-to-wall coverage, people stepping outside at night just to stare. So it's time to find out the truth about what comes after that spectacle, because the real danger does not arrive in a single flash. It unfolds slowly as high-energy photons and then cosmic rays grind away at our atmosphere over months, years, and even centuries. Years in the blast, ozone holes, UV storms, and cosmic ray showers. So, what actually happens to our air when that slow atmospheric grind begins? This is where the fireworks in the sky quietly turn into chemistry in the stratosphere. High-energy photons from the supernova arrive first, followed by a long drizzle of cosmic rays. When they slam into the upper atmosphere, they do something subtle but profound. They break apart stable nitrogen and oxygen molecules. Free atoms and fragments recombine into reactive nitrogen oxides, like NO and NO, which act as tiny chemical chainsaws. They catalyze the destruction of ozone over and over without being used up. This means one nearby dying star can reprogram the shield that makes Earth's surface habitable. Models give us numbers, not just nightmares. For a core collapse event at roughly 10 to 20 light-years, simulations suggest global ozone depletion could reach tens of %, not just a thin seasonal hole, but a sustained thinning of the entire layer. The polar regions, already vulnerable, are hit hardest, with losses that might double or even triple the amount of harmful UV radiation reaching the ground. It should be noted that these effects would not vanish in a week. We are talking about years, perhaps a decade or more, of an altered atmosphere. What does that mean for life at the surface? In the hunt for alien life, we treat ozone as a protective signature, and for good reason. Increased UV is brutal for DNA. It raises mutation and cancer rates, damages eyes, and disrupts delicate cellular machinery. In the oceans, the first victims could be phytoplankton near the surface, the microscopic plants that anchor marine food webs and help regulate our climate. On land, crops and wild plants would face chronic stress with stunted growth and damaged leaves. Animals, including us, would see higher risks of skin cancer and cataracts. But while this is serious, it is not an instant kill switch. It is a long, global stress test, pushing ecosystems and species toward adaptation, migration, or collapse over generations. generations. At the same time, the cosmic ray showers themselves intensify. Each incoming particle triggers a cascade of secondaries, including fast-moving muons that can penetrate hundreds of meters into the atmosphere, rock, and even the upper ocean. Background radiation doses creep upward worldwide, not enough to fry everything, but enough to matter for long-lived organisms, for embryos, for deep-time evolution. Optimistically speaking, this extra radiation might even slightly accelerate genetic experimentation in the biosphere. So, let's begin to see the pattern. Earth has almost certainly faced this kind of insult before, and survived. Our planet and its intertwined system of air, ocean, and life is remarkably resilient. The real question now is not whether biology can cope, but whether a technological civilization with satellites, power grids, and global agriculture can ride out years of enhanced radiation and atmospheric disruption without unraveling. So it's time to find out the truth about that vulnerability next. Civilization under a new sky, tech, climate, and human survival. So, what actually happens to a technological civilization when the sky itself turns hostile? Our ancestors watched the stars mostly for stories and seasons. We watch them with satellites, power grids, and a global internet that quietly assumes space will behave. A nearby supernova would test that assumption very quickly. The first to feel it would be our machines in orbit. A surge of high-energy particles would wash through Earth's magnetic shield, peppering satellites with tiny electrical scars. This means guidance computers might glitch, memory bits could flip, and solar panels would steadily darken as their crystal structures are damaged. We already see mild versions of this during strong solar storms, when operators switch spacecraft into safe mode. But while a solar flare lasts hours to days, a supernova at say 20 light-years could elevate the particle background for years. Could we adapt? Probably, but not comfortably. We would have to harden critical weather, navigation, and communication satellites, power some down for long stretches, and shift more infrastructure to fiber on the ground. It should be noted that the timing would not be perfect. Exactly when we most need accurate climate and radiation data, our best sensors would be under siege in the very environment they are trying to measure. Down in the atmosphere, the effects would be slower, but deeper. Extra cosmic rays punching into the air would trigger more chemical reactions, trimming back the ozone layer and subtly changing how clouds form. More cloud seeds in some layers, fewer in others. Slight shifts in where sunlight is reflected versus absorbed. The result would not be a single global freeze or bake, but an uneven reshuffling of temperature and rainfall patterns. For agriculture and water management, that is almost worse. How do you plant crops when the monsoon moves, or when Midwestern storms strengthen, while Mediterranean droughts lengthen? Human bodies and habits would have to change too. With ozone weakened, surface ultraviolet would rise, sunburn times would shorten, rates of skin cancer and cataracts would climb unless we responded with better clothing, sunscreen, and building design that filters UV. Entire cultures that celebrate outdoor work and festivals under open skies might shift towards shaded streets and twilight schedules. In the hunt for alien life, we often talk about atmospheres as simple shields. Here, we would feel, very directly, what happens when that shield is thinned but not removed. And psychologically, some societies would double down on science, monitoring radiation, breeding hardier crops, and coordinating global responses. Others might see the bright, unfamiliar star in the sky as omen rather than object, feeding apocalyptic movements and social tension. Yet, optimistically speaking, this is not instant doom. Even at 10-20 light-years, Earth's surface would remain broadly habitable. Coastal ecosystems, coral reefs already stressed by warming, and complex food chains would suffer. Power grids, already vulnerable to geomagnetic disturbances, would need rapid upgrades and smarter failsafes, but our choices would matter more than the blast itself. With coordinated adaptation, radiation-hardened tech, international data sharing, new farming zones, we could ride out decades of elevated risk. Here is the strange good news pattern interrupt. Without supernovae, there would be no iron in your blood, no gold in your electronics, no rocky planets at all. The same violent deaths of massive stars seeded the universe with the heavy elements that make Earth-like worlds and biological chemistry possible. So, let's begin to see a deeper symmetry. The catastrophe that might challenge our future is also the process that created us. But creation does not guarantee protection. The real test is whether a species that grew up under a calm blue sky can remain stable under a harsher, brighter one. So it's time to find out the truth about how we would detect, prepare for, and possibly even forecast such a stellar disaster long before it arrives. How worried should we be, really? So, after all this talk of stellar death, we have to face the uncomfortable question directly. Is a nearby supernova actually something we should be afraid of, or is it more of a distant background threat in the grand story of life on Earth? To answer that, we need to be precise about distance. There is a rough danger zone where a core-collapsed supernova stops being a spectacular light show and starts to seriously damage our atmosphere. Most studies put that zone somewhere between about 10 and 30 light-years. Inside it, intense gamma rays and cosmic rays can erode the ozone layer. Outside it, the effects fall off dramatically with distance. So, let's begin with our own neighborhood. Within roughly 30 light-years of the Sun, the local system of stars is surprisingly calm. We find the Sun itself, many red dwarf stars, and a few Sun-like stars, but no known giants with enough mass to undergo a core collapse supernova anytime soon. This means that, as far as current data show, there is simply no star close enough and massive enough to pose an immediate, civilization-threatening risk. What about the famous names? Betelgeuse, Antares, Spica, Eta Carinae. They are all real supernova candidates, and they will explode. But while they are dramatic in the night sky, they are comfortably far away, tens of light years beyond the danger radius, and in some cases thousands. When Betelgeuse finally goes, it will rival the moon in brightness, but it will not strip our atmosphere or sterilize the planet. It should be noted that there are uncertainties. Stellar evolution models have margins of error, some stars have poorly known masses or hidden companions, and there could be undercharacterized systems just beyond our local bubble. But astronomers actively monitor likely progenitors, track their spectra, and even watch subtle changes in their outer layers. We do not see a ticking bomb quietly waiting within 30 light-years. So how worried should we be, really? On human timescales, centuries to millennia, the odds that a supernova inside that critical radius will go off are extremely low. Optimistically speaking, other risks, from asteroid impacts to our own technological choices, dominate the near-term threat landscape. But on geological timescales, the picture flips. Over tens to hundreds of millions of years, the Milky Way's rotating system of gas, dust, and stars almost guarantees that Earth will experience damaging supernova events again. Isotopes like iron-60 and ocean crust already whisper that this has happened at least once in the last few million years. So it's time to find out the truth about what this means for a technological species. If the universe writes some of its biggest risks on cosmic timescales, how do we plan and even emotionally prepare for disasters that may not strike us, but might shape the distant descendants of our civilization? In the hunt for alien life, that question may matter just as much as the explosions themselves. Living in a galaxy of explosions, what this what if really tells us. So if supernovae can threaten a civilization spread across a planet, what does that really tell us about our place in the universe? We started with what sounded like a simple puzzle. If a nearby star explodes, is it a spectacular light show or an extinction-level reset button? So, let's begin the recap of where the data has actually led us. We found that the answer is not a simple yes or no. It depends on three things working together: distance, energy, and the quiet strength of Earth's atmosphere. Inside roughly 10 to 30 light-years, a powerful blast can strip ozone, flood the surface with ultraviolet radiation, and shake the climate. Outside that danger zone, the same event becomes a cosmic fireworks display, bright enough to rewrite our night sky, but not our biology. It should be noted that this is not just theory. We have radioactive iron-60 in Earth's crust that almost certainly came from a modestly close supernova in the last few million years. Life noticed. It may have stressed ecosystems, perhaps nudged extinctions, but it did not sterilize the planet. This means our atmosphere, magnetic field, and deep oceans are not fragile glass. They are armor that has already taken a hit and held. And our specific neighborhood? Optimistically speaking, it is relatively calm. The famous ticking time bombs you might worry about, like Betelgeuse, are hundreds of light years away. Spectacular when they go, but not lethal. Within that 10-30 light-year danger zone, we do not currently see any massive star poised to explode. We live in a galaxy of explosions, but our local system is, for now, in a quiet lane. Yet we are not just passive targets. Before the light from the next nearby supernova even reaches us, a ghostly wave of neutrinos will wash through the planet. Detectors like Super Kamiokande and IceCube are waiting for exactly that whisper. They are our early warning system, able to shout to the world that a star has died hours before the sky itself changes. And there is an existential twist. Those same explosions that can erode atmospheres also forge the heavy elements that make atmospheres possible in the first place. The iron in your blood, the calcium in your bones, the gold in our electronics, all were cooked in ancient stars and scattered by supernovae. We are, quite literally, the universe's way of thinking about its own detonations. So it's time to find out the truth in our own sky. Go outside on a clear night and track down Betelgeuse, or another bright, massive star. Follow the quiet work of those neutrino observatories. Support missions that map and monitor the stars in our neighborhood, because in the hunt for alien life and in the effort to protect our own, those maps matter. The next time a star in our galaxy dies, we will not watch as helpless bystanders. We will watch as a species that understands what is happening and can tell the story. If you want to explore the next big what if written in the night sky, stay with this channel, subscribe, and let's keep reading the universe together.